In this video, I want to show you how you can specify the strictly parallel measurement model of classical test theory in Mplus. Sometimes we want to test whether our measures satisfy the assumptions of the strict parallel model in classical test theory, because that can simplify our analysis, or simply we want to find out about the measures, whether they are parallel, whether they can be used completely interchangeably. And so one advantage that the strictly parallel model has, for example, is that then the test score variables would all be equally difficult and would also have equal reliabilities, because the model of strictly parallel variables implies equal means of the variables, and it also implies equal variances and equal covariances, and so as a result also it is implied that the variables then have equal reliabilities. And so with Mplus we can test that. We can test the strictly parallel measurement model of classical test theory. I want to show you this here for an example where I have 4 test score variables, y1, y2, y3 and y4 here in my data set. And so what I'm going to do in the model statement is I'm going to introduce a common true score variable that I call tau. That's a factor. And so the model of strictly parallel variables implies that all variables have equal loadings. So I'm fixing the factor loadings all to 1. Furthermore, the model also implies that all variables have the same means, and so that can be implemented in Mplus by setting all the intercepts or additive constants of the measurement model to 0. Furthermore, I'm estimating the common mean of the true score variable, and so since there's only this one parameter related to the mean structure now, it's implied that all variables have the same mean, because we're not estimating any intercepts for the observed variables. All the intercepts are fixed to 0, and so as a result this model has the constraint that all variables have the same mean. We're also estimating the true score variance component, which is relevant for estimating reliability, so that's the variance of the true scores. And then also we are constraining the measurement error variances to be equal by listing the variables here y1 through y4 and putting a label in parentheses behind the variables, and that holds the error variances equal across those 4 variables, which is also an implied constraint by the model of strictly parallel variables. So as a result, this model will always have only 3 parameters regardless of the number of variables that you're using, because we're only estimating 1 true score mean or common mean, 1 true score variance, and 1 error variance regardless of the number of variables. So this model will always have only 3 free parameters. Now let's take a look at what we get in Mplus when we test this model for our set of 4 variables to see whether they are strictly parallel in the sense of classical test theory. And the first thing that we should check is the model fit. You can see that does not look good. So the chi-square here is highly significant. We get a chi-square value of 85, 11 degrees of freedom. That's not a good chi-square. Not even the ratio is good here of the chi-square value to degrees of freedom. Also the RMSEA looks really terrible, and CFI, TLI, I guess the TLI looks pretty good actually, but the CFI is a bit low, and also the SRMR is rather high. So this model doesn't fit. So these variables aren't parallel, and oftentimes you'll find that, because oftentimes that is an assumption that is too strict, because either the variables differ in their means, so they differ in difficulty, or they might differ in their error variances, so they might not have the same reliabilities, and or they may not have equal covariances. And so this model is very restrictive. It implies that the test score variables must have equal means in the population, they must have equal variances in the population, and they must also have equal covariances in the population. And so now this would show you that you would have to work more on these tests if you wanted them to be strictly parallel. This set of variables does not yet satisfy this assumption. Now let's still take a look at the output and see what we get in case the model did fit. What would we get from the output? And so here you can see that the common mean parameter is given, so it's assumed here that all variables have equal difficulty. That could be a reason why this model didn't fit, because maybe the variables had different means. We can take a look here at the descriptive statistics, and you can see that the means differed a bit, at least with regard to the first variable. The first variable seemed to be easier. People got more points on average on the first test than they did on the last three, so those means are relatively similar here, but then this one is significantly higher. We can show that. So if we tested that for significance, we would find that that mean is significantly higher than the other ones, and that alone is enough to reject the strictly parallel model, because under the strictly parallel model there cannot be any significant differences in the means. Furthermore, we get the variance of tau, so that's the common variance here, and or the common true score variance, and so this would be the common covariance of the observed variables. And now if the observed variables differed in their covariances, that could also be a reason why this model didn't fit. And then furthermore, you can see we get a common error variance, because the error variances are set equal for all variables or across all variables under the strictly parallel assumption. And so again, this could be a reason why the model didn't fit, because maybe the variables are not equally reliable. They have different amounts of measurement error variance, and then also that could be a reason why it didn't fit, or it could be a combination of different things. So let's take a look at what we get in the standardized solution. You can see the model implies that all the standardized loadings are also equal, and that's because we have the implication of equal variances, and the loadings are all fixed to 1 in the unstandardized solution. And then there's also, it's implied by the model that all variables have the same variances, and therefore those standardized factor loadings are also the same under the model. Now here, if the model did fit, those loadings would be relatively high, 0.8, so that points to the fact that these variables are relatively reliable measures of this common true score factor. The standardized loadings squared give you the reliabilities, and in Mplus you find that in the section for r squared for the observed variables. You can see those r squared values are all also the same for the variables, and they are equal to the squared standardized loadings. Now again, under the model of strictly parallel variables, it is implied that all variables have the same reliability, and that is one thing that makes this model useful and simple, because then you know when you have different parallel tests, then they're interchangeable with regard to measurement precision. They all show the same precision for a given population. So in this case, if the model fit the data, then we would conclude here that 63.6% of the observed test score variance is reliable variance or is true score variance, whereas the remaining 36.4% that are given here under the standardized residual variances, that is the error variance component. So about 1/3 of the variance, a little bit more than 1/3 of the variance is error variance in these measures, whereas about 2/3 of the variance represents true score variance. Now, of course, we can't trust these estimates here because the model didn't fit well, so we would have to find a different model of classical test theory. Maybe we should try a less restrictive model, such as the essential tau equivalence model or the congeneric model, and so those models might fit those data better. If you're more interested in learning more about classical test theory and how to test measurement models, then check out other videos here on this channel. I have more videos on classical test theory, and also in the description you can find courses on measurement theory and measurement models that I offer. Please leave a comment in the comment section, subscribe to this channel, and I see you next time.